back to this slide here, which is showing you the code that we're running for the first time in SAS. So this is the code here, from the title to run statement, which is going to produce output like this table that's giving you the frequency and cumulative frequency in percent and cumulative percent, of course. As a reminder, we're looking at a binomial proportion for cure when it's no, so a no proportion, and at 0.2, which you can see up here, 20%, with a sample size of 10, as you know, 8 plus 2. Now you're going to say, interestingly, why are we looking at 0.2? Well, when we run this software and we want to do the binomial distribution, it's going to alphabetically sort your outcome. And in this case, cure, no and yes, no comes before yes, and so it sorts it in this way. And then just because it's sorted in that sequence, it's going to look first at no 0.2. So 0.2 is the proportion of no for cure, and it represents the sample proportion for no. And so what SAS does is it wants to give you a confidence interval or confidence limits around your sample proportion. The ASE here represents what's called the asymptotic standard error. We need the standard error in order to calculate the confidence limits. In this case, as we've seen in the previous slides, you can approximate the binomial distribution using the normal curve, the area under the normal curve. And that's what the asymptotic standard error represents. And they calculate it for you here. In a binomial distribution, and we'll see this in the next few slides, the standard area, the standard deviation for that matter as well, is by definition known in a binomial distribution. So down here are the exact confidence limits, which are derived from the exact calculations as we've been talking about in the past slides. And you'll see that they're actually broader than when we use the asymptotic standard error. And we'll go over that a little bit later. Why? And mainly it's because you have a small sample size, and therefore the approximation is not as accurate. It's not as appropriate to do, and that's why you get a less close result. Now, if we want to know whether or not this proportion of 0.2 for no is significantly different than the null hypothesis of 0.5, we need to test that. And that's what SAS does over here. It's a test of the null hypothesis where the proportion is 0.5. And very simply, what it does is it performs either a z-test here or an exact test down here. And we'll go over these the differences between these tests later on in the course. But essentially what we need to look at is what would be the probability of, in this case, 2 or less. Because remember, in I think it was slide 21, where we showed the table of the results of all the probabilities for all the distinct different results we could get when we had 10 trials, and you could have no heads or 1 head or 2 heads or 3 heads or 4 heads or 5 heads all the way to 10 heads, and then we added all of those cumulatively, and it went from 0 to 1. If you remember the 2 tails, so 2 or less or 8 or more, each probability was 0.0547. If you go back to slide 21, you'll see that. And if you add them together, you have a two-tailed or two-sided probability of 0.1094. So what does that mean? Well, it means that it's not statistically significant because, as we've seen over here in the confidence limits actually contain the null hypothesized proportion of 0.5. So this confirms that we fail to reject the null hypothesis, and the p-value is greater than 0.05. So what is this standard error, and why do we need it? So we saw in the previous slide that the standard error is useful because we use it to calculate confidence limits, and we also use it to perform a test of significance. But what is it? So really what it is it's the size of the variability between sample proportions that are repeatedly selected from a population. That's the standard error. So if you were to repeat the test, if you wish, or the sampling of your 10 patients and measure the proportion again, what the standard error represents is the variability that you can expect between each of those samplings. Fortunately, with the binomial distribution, the standard error is known by definition, and that's because we're working with a discrete variable, discrete data. The standard error is simply the proportion of the observed event, the one you want, so 0.8 in this case, multiplied by 1 minus that proportion, so 1 minus p, which we call q, and that's 0.2, divided by n, and it's the square root of that. Now, the standard error of a sample proportion under the assumption that the probability of success is p is, in this case, because the probability of success that we are testing against, for instance, is 0.5. So in this case, it is capital P, which is 0.5, times 1 minus capital P, which is Q, which is 0.5, divided by n, and it's the square root of that. That is how you obtain your standard errors. Now, if you remember in the previous output from the SAS output from the freak procedure, the standard error of a proportion was reported twice, and I pointed that out in the slide. So first was the observed proportion, or the sample proportion, which was p equals 0.2 for no, because no came before yes. If we had flipped it around, it would have tested it for yes, which would be 0.8. And then next, if you remember, it was on the right of the slide, the proportion expected under the null hypothesis were p, capital P, equals 0.5. And in both cases, n of course, equals 10. So if we do the calculation ourselves, we'll see that the standard error is equal to 0.2 times 0.8 divided by 10, and the square root of that is equal to 0.1265. And if you go back to the slide, you'll see that that's exactly what SAS reported. And for the null hypothesis, we get 0.1581. And once again, if you look on the right side of the slide, you will see that that's what the standard error was calculated for by SAS. So as a refresher, you'll remember that SAS calculated the exact confidence limits, the 95% confidence limits, and they were found, and this was for the proportion of 0.2, the sample proportion of 0.2, and you'll remember that the range of the confidence limits included 0.5, which is our test hypothesized null hypothesis value, that when we tested using the exact test, we also found that if we took the two probabilities from each tail and added them together, we got a value of 0.1094, which of course is greater than 0.05, which is our alpha. And so with a two-tail p-value of 0.1094 and the 95% confidence interval that contains 0.5, then we fail to reject the null hypothesis that p equals 0.5. So now what if the research scientist discovered an error and corrected it, and in doing so changed that proportion of no to 0.1? So you'll see here in this slide that the code remains the same. However, what we're putting, of course, is we have 1 no and 9 yeses, but everything else stays the same. However, what does change are the results. So if you look at the exact confidence limits, the range now is 0.0025 to 0.4450. And you will immediately note that this does not contain the null hypothesis proportion or probability of 0.5. When we test whether the proportion observed is significantly different from our null hypothesized proportion of 0.5, we see that the probability one-sided is 0.0107, and that when we consider both tails and we add them together, we get a p-value of 0.0214. So when the p-value is less than 0.05, the confidence limit does not include the null hypothesized proportion of 0.5. So in conclusion, we can state that if this result is due to chance, the probability of getting 9 or more successes for the new drug is 0.007, and the probability of getting 1 or fewer successes is also 0.0107. So the two-tailed p-value of the sum of those two, 0.0107, which is 0.0214, is the probability of getting a result as extreme or more extreme than the observed difference under the null hypothesis that the difference was due to chance. That is, p equals 0.5. Now, we would report that 90% of the patients cured on the new drug is significantly greater than the null hypothesized proportion of 0.5. P equals 0.0214, and the 95% confidence interval of 0.0025 to 0.4450. Now, just as a note, which you'll see that we repeat ourselves many times in this course, is that the 95% confidence interval does not contain the hypothetical probability of 0.5. So this brings us to the end of Lecture 1. I hope you liked it. Next up, in Lecture 2 of Part 1, is the central limit theorem. See you soon.